Yeah, let's start for now. You can see the PPT, right?
Yes.
Yeah, so I think this was one of the homework questions, and I hope everyone has solved this. So I've just put the answer here, and I think we had discussed about how to solve it in the last class. So I will not go through with the solution for this one. If you have not done it, please do it after the class. And so today we will be doing questions from dynamic similarity. So I could find couple of questions which had come in previous years, and I'll tell you, if you get lucky, you will get a question from this topic. This is very straightforward. Just need to use equate the Reynolds number in a model in a prototype. That's what dynamic similarity is. And once we are done with that, then we will look at a question from drag force, and then do some questions from flows over a flat plate, and then how boundary layer is generated, and the boundary layer thickness and all of those things. So let's get started. This is from GATE 2016. The question is, oil with some kinematic viscosity flows through a pipe of 0.5 meter diameter with a velocity of 10 meter per second. Water, now having a different kinematic viscosity, is flowing through a model pipe of diameter 20 mm. For satisfying the dynamic similarity, the velocity of water is. So, as I just told you, that for dynamic similarity, the Reynolds number have to be same. So, let's say here this
Have
M,
to equate the model with prototype.
yeah, exactly. So, P here is prototype, and once you equate these Reynolds number for model and prototype, knowing that that is the formula for Reynolds number for, in a pipe flow. So this is rho Vd over mu, where d is the diameter, rho is the density of the fluid, v is the velocity, and mu is your dynamic viscosity, and you can convert it into kinematic viscosity because that's what has been given in the question. So this will be v velocity, d diameter, and mu, which is the kinematic viscosity, and v mu, sorry, nu is given as mu over the density of the fluid. So I guess once you know that, then it is very straightforward to solve this. Please solve this and tell me what you get. So again, I'll just write down here that RE for prototype, oh, yeah, RE for prototype has to be equated with RE for model.
.2.
Yeah. So yeah, everyone got it right. This is 22.25. So I'll just write down the values here for completeness. So this is VD over mu1, V2, D2 over mu2, and we are after this mu2, oh sorry, V2. So V2 is what we need to find, and you can substitute the other values here. So velocity for oil is given as 10 meters, diameter is zero point 0.5, whereas the kinematic viscosity is 10 raised to the power minus 5. V2 is what we need to find. D2 is 20 into 10 raised to the power minus 3, and mu here is 0.89, 10 raised to the power minus 6. So you can solve this, and then you'll finally get to this 22.25. Yeah, so this is like a 2 marks question, as easy as that. And So on a similar note, let me see if you guys can do this one. This is again the same concept was but asked in a slightly different fashion. So for a laminar flow of water over a sphere, the drag coefficient CF is defined as some formula. So this is drag force divided by rho u square d square, where F is the drag force, rho is the flow density, u is the flow velocity, and d is the diameter of the sphere. Now the density of water is 1000. When the diameter of the sphere is 100 mm, 100 mm, the fluid velocity is 2 meter per second and the drag coefficient is 0.5. So one configuration is given. And if water flows over another sphere of diameter 200 mm under dynamically similar conditions, the drag force on this sphere is. So again, they have mentioned that this is dynamically similar conditions. So you will have to first equate the Reynolds number, get the velocity, and then from this velocity use this formula with the drag coefficient being 0.5 to get the drag force. Yeah, the same theory applies here. And yeah, please try to solve this. I'll just write down whatever is given to us. So CF is given as 0.5. That's the drag coefficient. Density is 10 raised to the power 3 since it is water. Now D1 is 100 mm. V1 is 2 meter per second. D2 is 200 mm. V2 is not known to us. And yeah, it's the same fluid, so density really does not change. You just need to find V2 using RE1 equal to RE2 since they are dynamically similar. And then calculate the force in newtons. So once you have V2, you just need to do this. F will be CF times rho V2 square D2 square.
20, sir.
Yeah, I think this is correct. So it should be around 20 newtons. Right, so I think it's very similar to the last one. I'll just move on to the next one. Now this is from GATE 2016, and let me see if you can answer this. So the instantaneous streamwise velocity of turbulent flow is given as follows. The time averaging of the fluctuating velocity u prime is. So if you have studied little bit of turbulent flows and how you do Reynolds averaging, this will take you like 2 seconds to solve.
0.
Yeah, this is right. So I guess people who have not studied turbulent flows, you can simply think of it like this. So there is some flow which is a function of x, y, z, and t, and you can break this flow down into a mean component. So the mean component is called the time mean component because the time variation goes away from here. And then there is this fluctuating component which is called as the eddy component, or yeah, the time varying fluctuating component. And this u bar is defined as the time average of your total velocity. So this is x, y, c, and t, dt. So that's how you define u bar. Now, when they ask you to calculate the time averaging of the fluctuating velocity, you can do this. So basically, they are asking you for something like this, u prime dt. Now this u prime, you can use this and say that u prime is nothing but u minus u bar, and then you integrate over dt.
Sir,
Yeah.
is that for all of the axis, like x-axis, y-axis, and z-axis, or like only for x-axis?
What do you mean by only for x-axis?
A turbulent flow, and where it would be zero, like only for x-axis or y or z
No,
on
this is
all
a
of that
general
axis?
result. You mean u velocity, v velocity, or
Sir.
no, no, no. This is a general result. This will be true for all u, v, w, because that's how you define your fluctuating component. So it's inherent in the definition that the time mean of this fluctuating component will be zero. We will see this through this small manipulation of u prime. So this is u prime, and you can write this as u minus u bar of dt, and then you have 1 over t integral u dt minus u bar dt, right? And then I guess you can absorb this 1 by t inside the bracket, so and use this information. So let me just make it explicit. So 1 over t integral u dt minus, since u bar is not a function of time, you can take this out of the integration. You have 1 by t here, u bar goes out of the integration, and okay, this should be for the time period capital T. So yeah, then this becomes u bar times dt. This by definition we already know is u bar. Uh, like we can use this here and say that 1 by t u dt is nothing but u bar minus, this is 1 over t u bar, and then integrating 0 to 2 dt will just give you t, which cancels out, and then u bar and u bar, if you take the subtraction, will be 0. So you have just shown that the time averaging of the fluctuating component over some fixed time period t is equal to 0, and that's what they had asked in the problem. So this is actually inherent in the definition, but yeah, if someone does not know it, they can proceed through this small manipulation of the initial u velocity. So Vijit, is this fine, right? Because you can
Yes, sir.
similarly define, let's say some v, which is a function of x, y, z, and t.
Uh-huh.
Then you can say that v can be broken down into the time mean component plus the fluctuating component. And then similarly, you will find that the time averaging of this will be 0, will be equal to 0, and you can do it for w velocity also. Yeah,
Okay.
yeah.
So here U bar is constant, sir.
U bar is constant in time, U bar is not constant in space.
So is there any space means different
Yeah,
concept?
so people also do Reynolds averaging on in space, so so this is a matter of choice for you. So you can also write this as U is some let's say some U this thing, so square bracket, so and the square brackets represents the so let me just write it here, U as some 1 over L integral U dx 0 to L plus again some u prime. So I am writing hat because this is not the time fluctuation now, this is x direction fluctuations, right? So this will only be a function of y, z, and time. So it's a matter of convention, but this will not be as useful as this, because here you have completely eliminated the time dimension. Here you still have some space dimensions. So while doing solving Navier-Stokes, I don't know if you guys have heard of something called as RANS. So that is called as the Reynolds average Navier-Stokes equation.
Yes, sir.
Yeah. So
Uh,
there they will have like decomposition of U in time constant flow, which is also called as sometimes called as the background flow, plus the time fluctuating flow, which is that U prime. So is this fine, Suraj? You get it right?
Yes, sir. And please, can you explain the model and prototype because there is confusion for me.
Uh, so I mean, so that you can go into like deeper theory of what is a model and what is a prototype. The basic idea is you have, let's say, a model of a ship, but you cannot do an experiment on a full big ship, right? Let's say you want to study, or instead of a ship, you take wing of a plane. Doing experiments on the whole wing of that plane is difficult. So what you do is you make a prototype which has similar dynamic conditions as your model. So let's say the ratio of width is to length is same, and the flow which you are so let's say Re, which is a function of, so this is rho v d over mu, right? So I'm saying if I have a wing of a plane, I can't do experiment on the whole that big wing. What I will do is I will make the flow conditions similar by adjusting v and d in such a way that uh, I get the similar Reynolds number, and then I can study the behavior of this this prototype experiment on this prototype, and then based on those results I can analyze the actual model, which is like a big structure. So that's what it is based on. And so if you decrease the diameter of the length scale, you have to increase v in order to keep the Reynolds number constant, because in the end you will be concerned with what kind of Reynolds number flow are there when the plane is flying, and that based on that you can change the length scale and the velocity scale for you.
So for dynamic similarity, Reynolds number will be same, but drag drag force will be different. No?
uh Drag force can be different, but I think you're talking about this example, right? Here we
Yes, sir.
yeah, we took that the drag coefficient. Oh, you mean the drag coefficient, I think, not the drag force.
CF. Ah, yes.
Yeah. So I think you are right. The drag coefficient can be different, but here they have not mentioned anything. So you have no choice as to what to assume drag coefficient, because see, drag coefficient will depend upon the surface of your body, and what kind of surface friction you have, and the roughness of the body. And since they have not specified anything, I guess the best option is to just take CF to be same for the model as well as the prototype.
Okay, and means logically this the force will be different because it is small and it is big.
No, uh yeah, if you think about the force, yeah. So U and D will be adjusted in a way that Reynolds number stays the same, but the force will be less, of course, for a smaller body. Yeah.
And from model and prototype term, model stands for actual means real
Yeah.
things.
Model stands for the real things.
Okay, sir. Thank you, sir.
Yeah. Okay, let's. So this, I think this is clear. We have done this already. And so, on a similar note, let's see this example of a question from the drag forces. And this was from GIT 2019. The aerodynamic drag on a sport car depends on its shape. The car has a drag coefficient of zero point 0.1 with windows and roof closed. With the windows and roof open, the drag coefficient becomes zero point 0.8. So when you change the configuration by opening doors and roofs and window, you change the shape and then the drag coefficient increases somehow. Now the car travels at 44 km per hour with the windows and roof closed. For the same amount of power needed to overcome the aerodynamic drag, the speed of the car with windows and roof open is, again they want it in kilometers per hour, and they have given some assumption that the density of air in frontal area may be assumed to be constant. So this is again, I guess, straightforward
Mm.
once you know that power.
Drag coefficient rho v square by 2 and power for by applying power force into.
Yeah, I think you are right, Abhijit. So try to solve this and give me the final answer. And for people who have not followed this, then okay, power is given as the drag force times the velocity. So this is like the conventional formula for power, force time velocity. Where let me just write it. This is the velocity, and this is your drag force. So that amount of force, that amount of power is taken up by the drag force, and then the same amount of power has to be supplied to the car in order for it to run, overcome the drag force. And also this drag force is defined as CD, which is like your drag coefficient, times half rho av square, where a is the area normal to it, and v square is your velocity. So yeah, I think that's all you need to solve this. Let me, yeah, go to the question and write down what is given to you and just give me the answer. So drag coefficient 1 is zero point 0.1, and this is when the the windows are closed. And for that configuration, we have been given that velocity is 44 kilometers per hour. Now, drag coefficient for 2 is given as zero point 0.8. Velocity is what we need to find. And you just need to know that, so they have said that the power is same amount of power needed to overcome the aerodynamic drag. Ft times v, where the drag force is given as CD times rho av square.
Is it 47.40?
I think you will need to check your calculations because that's, I don't think that is correct. You will get a nice number actually. I mean, not in decimals, I think. So did you take v square into account? Sorry, FD times v.
Yes.
Okay, then just recheck your calculation. Might be,
So 21.89 is I'm getting.
yeah, this is right, but why are you getting 21.89? You should get exactly 22, I feel. Did
Yeah,
you do
don't know.
some approximation somewhere while calculating?
Yeah.
Where? You don't need to approximate anything here, right?
So no, I'm putting all the values like similar, but why I'm getting?
Yeah, you should not get 21 point something. Should be exact 22. Okay, this might be
Okay,
20.
okay,
incorrect.
okay. I made a mistake.
Okay.
Is the answer 22, sir?
Yeah. Yeah, this
Yeah.
is right. So I guess some people immediately when they say c kilometer per hour, they immediately do this 5 by 18 business and then convert it into meter per second somehow. That is not always required, because in this case one everything in the end has to be converted back to kilometers per hour. And also, so in this question we will be doing something as like p1 is equal to p2, and then all the other units get cancelled out. So you can actually have velocity in kilometers, and maybe if you have density in meter, or some length scale in meters, so that can be there. But okay, I mean, let's just see how to solve this. So P1 has to be equal to P2 because the same amount of power is needed to be supplied. And P1 we can just write FD, which is CD. So CD will be zero point 0.1 times rho times A times V square, which is given as 44 square over 2. And then you have one more V, so there will be 44 cube actually. And similarly, this will be zero point 0.8. Now rho times A will not change, because you can assume that the density and the frontal area are same. So that makes our life very easy. And this will again be some V2 cube. That is what we need to find. And this will be 2 again. So this, and this you can cancel immediately. Now this becomes 44 cube over 8 cube. You can remove the decimals from here and here, and this is equal to V2 cube. So see how nicely this is in a cubic form. So wait, did I do something wrong here? Oh, you can write this as 2 cube, sorry. So this should not be 8 cube actually, this is just 8. So yeah, 2 cube, and then okay, maybe we can say this is 22 cube. So V2 has to be 22 kilometers per hour. So I guess I will just remind you guys again that, see, you will know the formulas, you will know the theory, but if you somewhere in between do some small error in the calculation, you'll get completely different result. And one reason in the GATE exam they have now introduced these NAT questions, numerical answer type questions, is to just check if people are doing their calculations right, because sometimes you make an error, but in those four options that final answer is not there, so you can recheck and find where the mistake was. But in such cases you are really, I mean, on your own, and if the mistake is there, then you won't be able to correct it. But yeah, I guess one thing you can also think is, okay, maybe Priyanka, you said 47 in before, right?
Sir, I took roots instead of cube root.
Okay. Yeah, yeah. So I just want to mention that you can also, when you write down the final answer, think about it. So since the drag has increased and everything else remains the same, the velocity has to go down also. So maybe you can, there is one way of verifying if what you have done in terms of calculation is correct or not. So yeah, if you get 47, then you should already get worried that okay, there might be some mistake, because as the drag increases, the velocity has to go down.
Okay, sir.
Yeah. So maybe we can move on to the next one. Yeah. Now let's try to look at flows over a plate and see the concept of boundary layer. So this first one is simple. This is from K 2016, and this does not really test any of your concepts of boundary layer, but just uh, mass conservation. So a steady laminar boundary layer is formed over a flat plate as shown in the figure. The free stream velocity of the fluid is u naught. So this is the free stream velocity. The velocity profile at the inlet AB is uniform, while that at downstream CD is given by, so some parabolic profile is given to us. Now the ratio of the mass flow rate m dot BD, so on this section, leaving through a horizontal section BD to that entering through the vertical section AB is. So something is leaving from here and something is coming from here, okay? Now we need to find the ratio of these two. So can someone tell me, according to mass conservation, what will be m dot BD or the mass leaving out of BD?
M dot AB minus M dot CD.
Yeah, that is perfect. So again, doing the mass conservation, you can say that this is your horizontal inlet, and at CD you will have a horizontal outlet. And if both of them are not same, something has to go from the other direction, which is the vertical direction, because at the bottom you have this flat plate, and there can be no penetration in this plate, so no mass will flow downwards. So everything which is left should go from BD. So that we have already established. Now this formula we all know by now. M dot is the density times the discharge, where discharge is rho VdA. Now all you need to do is to calculate m dot CD and m dot AB. So let's just write this. So m dot AB minus m dot CD, this is small d, has to be equal to m dot BD. So this is simple mass conservation. And if you calculate m dot AB, since the velocity is constant here, you can just write rho times q, which is area times u naught. Now the area for this is, let's assume some kind of thickness w. So in this dimension, let's, so you will have some thickness w here, and then delta is given to you, so that becomes the cross sectional area, and then u naught is there. So this is your m dot AB. Now things were simple here because the velocity was not varying with any of the space dimensions. Now if you try to do the same kind of thing for CD, you have to take some elemental area. So let's say I took this elemental area dy, and then you can just say that rho times m dot CD will be rho times A, which is A W. So width will remain the same, and then you will have some dy, that is your elemental area dA, times u, this small u, and you have to integrate it from 0 till the whole free stream, wherever you reach the free stream velocity. So from 0 till delta. So now rho and w can be taken out, and for u you can substitute this formula u naught. So this will be your m dot CD. Now I would like you guys to do this integration and tell me what m dot CD is, or better yet, just give me the ratio, because once you have m dot CD you can find m dot BD. So m dot BD will be just again m dot AB minus m dot CD, and then just tell me what the ratio is. So I am asking you guys to do it is because I want you guys to actually do solve these questions, practice, and that will reduce your chances of making mistakes.
CD is two-third of MAB.
Yeah, I think this is right. So if you get CD as two-third of MAB, then what will be the ratio of,
One third.
yeah, perfect. So then you can just say that this is MBD is one third of MAB, and then M dot BD over M dot AB becomes 1 by 3 or 0.33. Yeah. So
Given, yeah.
so finally you'll have to write 0.33 there. Everyone got it, or someone wants me to solve this integral? Okay, I think everyone got it. So if this is done, then let's move on to a couple of more questions. Now we'll actually look at the boundary layer. So this is from GATE 2018, set 2, question number 22. The viscous laminar flow of air over a flat plate results in formation of boundary layer. The boundary layer thickness at the end of the plate of length L is delta L. When the plate length is increased twice to its original length, the percentage change in the laminar boundary layer thickness at the end of the plate is. So in order to solve this, you will need to know some theory about the laminar flow over a flat plate. So I have taken this schematic from again Sengal. You see, whenever there is a flat plate and there is a flow over it, a boundary layer will be created, and this boundary layer here in this figure is given by the grayish shaded region, and above this boundary layer the velocity will be constant in y, which we will call as the free stream velocity. But inside the boundary layer the velocity increases as you go up in the boundary layer. So here at the end, close to the plate, there will be a no slip condition, which means that just adjacent or next to the plate the velocity will be zero, and slowly you see this vector increasing. So it was here, it was here, and then it was here. So this kind of profile is there, and then at the end when you reach free stream velocity, boundary layer gets terminated. So one definition of boundary layer is wherever the velocity reaches 99% of the free stream velocity. Let's say this was your free stream velocity u naught. Wherever the velocity in the boundary layer reaches 0.99 of u naught, that is where the boundary layer gets terminated. And so you can see that when the flow moves from a laminar to a turbulent regime, how the boundary layer thickness increases, and how the flow transitions based on the Reynolds number. So this has a very rich theory actually, but for the questions that I have seen in the exam, most of them are related to the thickness of boundary layer, and most of them are actually related to this equation called as the Blasius equation, which gives you an expression for boundary layer thickness. So this delta, let me just write it here. This is the boundary layer thickness, which will be just the vertical length of this gray area. So here this is this, and here this will be this, and you can see that the thickness is increasing as we go in x. And so this Blasius equation gives you an expression of boundary layer thickness based on the length at which you are and the Reynolds number. And here the Reynolds number is defined based on again the length of the plate, or the section of the plate in which you are. So let's say if this is my plate, this is my X. So as you keep going to the right, the X increases, and then based on that the Reynolds number increases, and thickness also will increase. We'll see that. So just keep this formula in mind. Actually, you don't even need to know this 5. You just need to know how the boundary layer thickness is proportional to your X. So that's all is needed in this question. Let me just write down the Bloss's formula again. So delta, which is the boundary layer thickness, is Ifx divided by Refx. Now this can be written as rho v x divided by mu, and you can just say that this, if the velocity does not change, then the boundary layer is thickness is proportional to x over root x, or delta is proportional to root x. So this is a very important result, which means that as you go further in x, as x increases, the boundary layer thickness also increases. And this is what you will need when you solve this question. So I guess just solve it and let me know what the final answer is. I've given you all the recipe to solve this.
41.42.
Yeah, this is correct. Yeah, it should be root 2 1 minus root 2 minus 1, right? Something like that. Yeah, root 2 minus 1. You're right, 41.42 should be the correct. So I'll quickly just tell you how to do this. So delta 2 over delta 1 will be equal to x2 over x1. This we got from here. And x2 for us is twice, so we say that when the length increases, so this will be root 2 x1 over the root of x1, so this gets cancelled. So you can say that delta 2 is root 2 times delta 1. Now they are asking you to calculate the percentage change, and we know that percentage change is nothing but the change divided by the original value times 100. So this will be root 2 minus 1 delta 1 over delta 1 times 100, and root 2 you should already memorize the value for root 2, that is 1.414, and if you take 1 out of it, so it will be 0.414, or you can just write 41.4%. And if you want it in 2 decimals, you can just write 2 here as well. Yeah, so that this was straightforward. And let's see one more example where now instead of having the boundary layer thickness, you have tau, where tau is the shear stress. So here I will just give you the relation actually. If we have already seen that this expression is there for laminar flow, we should also, yeah, let me just not write equal to, it's confusing. So delta is proportional to root x, whereas tau is proportional to 1 over root x. So that that information you need in order to solve this. And if you know this, let me know what option would be correct. So I'll read the question. Consider laminar flow at zero incidence over a flat plate. Basically, same configuration, horizontal flow. The shear stress at the wall is denoted by tau W. The axial position x1 and x2 on the plate are measured from the leading edge in the direction of the flow. If x2 is greater than x1, so
Seems like C.
yeah, I think you are right. So this is your x,
So
this is your boundary layer, and somewhere here you will have x1, and somewhere here you will have x2. So
would it be C, sir?
yeah, this is correct. Yeah, it has to be C. So here you will have tau at x1, here you will have tau at x2. Now, if you know this expression, meaning that tau is inversely proportional to root of x, then as x2 increases, the shear stress at the wall decreases. So this tau 1 will be greater than tau 2.
Hmm.
Yeah, so C will be correct.
Sir, for non-viscous flow, shear stress will be 0.
Yeah, I mean, so if you don't have viscosity, then there is no concept of boundary layer. That's why when we use when we say non-viscous flows or inviscid flow, we use the Euler's equation and not the Navier-Stokes equation, because there is no concept of viscosity in that, and then shear stress will only come when you have viscosity in the flow.
Okay, sir.
Yeah. So this is there, and then I guess let's move on to. Okay, yeah, I think we solved it here already. Let me just make it. Just take it here. Okay, so there is now another concept that you should know, and this is not. So if you have a boundary layer, you can also have a displacement layer, and related to the boundary layer, there is this displacement thickness, which we will see what it is, and that's what they are asking you to calculate in this one. So the velocity profile inside the boundary layer for flow over a flat plate is given. So some kind of velocity profile is given to you, which is a sinusoidal variation basically, where u infinity is the free stream velocity and delta is the local boundary layer thickness. If delta star is the local displacement thickness, the value of delta star over delta is. And so now, what is a displacement thickness? If you see, again, the schematic is from single. This dark shaded gray region is your delta star. So yeah, this will be your delta star, and the whole thing is delta. So this displacement thickness is basically accounting for the mass deficit which comes because you have shear in these flows, and the expression for it is this. So delta star is the displacement thickness, and it is an integral of 1 minus u over u from 0 till delta. So if you want to visualize, let's say, if you have some configuration like this is x, this is y, and your velocity profile is like this. So it's here, here, and here, and this is your free stream velocity. So you have some kind of mass deficit here. Let's call it m dot 1. Now, what if you had like a constant flow, and then you have this constant flow over some kind of depth, Now this, okay, this will be called your delta, and this, let's say, is M2. So for delta star, M1 dot has to be equal to M2. So basically what we are saying is the mass deficit here, I think we should color it with that. Yeah. So the mass deficit here would, if you flatten it out, make it into a constant thickness layer, then how much that delta star is the question here, and that gives you this displacement thickness. You don't really need to be concerned with this. Basically, you just need to know what delta star is in terms of delta and the velocity profile, and then you can do the computation. So I will, oh, wait, yeah, I'll write down the formula here again, and okay, just do the integration. It's very trivial. So delta star is given as integration 0 till delta 1 minus small u over capital U dy. The profile here is already given to you, which is u infinity is your free stream velocity. This is sine pi y over 2 delta. So please do the integration, guys. Tell me which option is correct.
1 minus 2 by pi b.
Yeah. They will get it. I think you probably would have, but in any case, let me also solve here. So we are doing this 1 minus u over u infinity, which is sine of pi y over 2 delta, and this is integrated now. So when you integrate this, you will get y minus sine will turn into, oh wait, you can have cosine pi y over 2 delta, and there will be a minus 1 here, so you can say that this is positive, and this will also be divided by pi over 2 delta, right? 0 and infinity, oh, not infinity, sorry, delta. So if you put the upper limit in, this will be delta plus of cos pi delta over 2 delta over pi by 2 delta minus 0, and then there will be one more minus where it says cos 0 over pi by 2 delta. So if you cancel this out, cos pi by 2 is 0, so this term will go away. This will be delta minus cos 0 is 1, and this will be 2 delta over pi. This is your delta star, and then I guess you can do this divide by delta both on sides. So this will be 1 minus 2 over pi. So only potential of making a mistake here is to not remember that integration of sine is negative of cos. Then I think there will be a difference of plus and minus, and then that will be an issue. But yeah, the correct option for this problem is B. So did everyone get it? Or did someone fall in this sine trap, integration trap, I said.
Yes, yes, sometimes
Yeah.
I make mistake on this kind of thing. I only make cos and then forget about this part.
Yeah,
And
so
then
these I think will come with practice only, and then I guess whenever you see integration with sine or cos, just be careful. Take 2-3 seconds extra, but make sure that you get the sign at the end of the integration correctly, because you know that these are like potential places where you can make mistakes, right? So, I mean, better to spend some few more seconds than to do it incorrectly, I feel.
hidden bit.
Yeah. Uh, yeah, I think so. That will be it for today. I think we have covered most of the questions that I could find, at least. Let me. Yeah, if you guys have any questions that you can ask. I guess in the next class we will do overall questions from maybe engineering sciences, fluid mechanics from engineering sciences. And once that is covered, then we will have a class of radiation, heat
Sir,
transfer through radiation. Yeah,
Yes, sir. Heat transfer is important.
yeah, yeah,
Fourier series and Fourier transform.
yeah. We will see that also.
Okay.
Yeah, Suraj, you had a question.
can you take that dimensional analysis part?
Yeah, I can do that, but the problem is I have not seen many questions from it in the pre. So it used to come very early, like 2000. If you see gate 2004, 5, 6. As for some reason they are not doing giving questions from. I think you are talking about this Buckingham Pi theorem and dimensional analysis sort of things, right?
Yes.
Yeah. Let me see if I can find some questions and then we can cover it, because I feel at this point of time, if the probability of question coming from that topic is so low, better not to go into it, because we have a few more topics that I would like to cover. But in any case, let me see if it can be covered quickly. Then maybe I can have one slide where we summarize most of the things from dimensional analysis.
Okay, sir. And from model and prototype, is there any other concept other than the dynamic similarity where Reynolds numbers are equal?
So
And
yeah, model and prototype, you can have things based on different kinds of non-dimensional numbers. So most of the time we have only talked about Reynolds number in our sessions, but there is something called as the Froude number, and there is something called as a Rayleigh number. So I guess what I'll do is I'll in the next class have one slide where I just put down all these different non-dimensional numbers, and for different cases you can have different kind of numbers coming into picture. So if the balance is between let's say the gravitational force, you will have a different non-dimensional number being important than the Reynolds number. So I'll summarize it in the next class.
So from Rayleigh method, can't we do the dimensional analysis?
No, but if
It
the
seems like I did.
dimensional analysis you will do
Do.
with Rayleigh number, but you mean Reynolds number, right?
No, no.
Ah, you are saying
Rayleigh
Rayleigh
method.
method. Yeah, yeah, yeah. that's up to you.
Actually, I was just recapitulating that with the term,
Yeah, yeah, yeah. No,
so
no, but
that's why it came
yeah,
in my mind.
no, no, no. Those are two different concepts actually. So Rayleigh number is
Okay,
they
okay.
are different. It's a number used when you have heat transfer, and I mean I don't know if you know about Rayleigh-Benard convection. There you have this non-dimensional number called the Rayleigh number, which governs the regime of the flow. But that is different than the dimensional analysis you do using the Rayleigh's principle.
Mhm.
Yeah.
Sir,
Okay.
and on topic of basics of compressible flow, what type of questions
I
can
think
come?
we have done it. So, only question that can come is mass conservation, where instead of having rho constant, so you have rho in the integration also. I mean, compressible flows means rho changes with time, right? Time
Yes.
or space based on that. So I think there the discharge flow can be different, and then you can't take rho out of the equation. So those sorts of things. But again, I have not seen many questions which have compressible flows. So I don't know what they will ask. Yeah. Any other doubts, guys?
No, no, sir.
If not, then I think we can stop here and we will continue with some questions in the next class. Yeah, I will again remind you guys, start giving test series and you have roughly a month left, right? So if you can give one test every day or every alternate day, you will still be able to give 15 tests, right? So that is, I think, a sufficient amount of practice if you can give 15 full length tests somehow or subject tests also.